Okay, so our final problem to wrap up momentum, we are going to talk about an elastic collision. In an elastic collision, we have conservation of momentum and also conservation of energy. Generally, our inelastic collisions are a little bit easier to work out with the math. The elastic collisions are a little bit more challenging. So we are going to work through this. I'm not going to ask you to do a homework problem about it, but I think that it's important for us to see what's going on here because it relates to something that I'm having you do in our conservation of momentum lab. Okay, so we have two billiard balls, pool balls, of identical mass, so M1 is equal to M2, and they move toward each other. The initial velocity of one of these balls is 30 centimeters per second. The initial velocity of the other one is minus 20 centimeters per second. So that means that one is coming in to the other direction toward the first mass, and they're going to collide, and then they're going to bounce off from each other. Momentum will be conserved and energy will be conserved. And so we want to figure out what is the velocity of each of these balls after the collision. So V1 final equals question mark and V2 final equals question mark. Okay, so in order to solve this, we have to use conservation of momentum and conservation of energy. We're going to do a lot of algebra here too, okay? So buckle in, let's go. With our conservation of momentum equation, okay, I'm going to just call that P over here. We've got M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. Okay, now if we know that M1, so this was conservation of momentum, the sum of our initial momentums in the system before the collision has to equal the sum of our momentums after the collision. Okay, so the mass is the same for all of these objects. So the mass we can just get rid of. We can divide everything by m. M is the same number. So we have V1 initial plus V2 initial equals V1 final plus V2 final. I'm going to call this equation 1. Okay, and for a reason you'll see here in a minute, I'm going to solve this so that I've got all the terms for V1, or for mass 1 on one side, and all the terms for mass 2 on the other side. So I'm going to say V1 initial minus V1 final equals V2 final minus V2 initial. So I just moved all the quantities going with mass 1 to the left, all the quantities going with mass 2 to the right. And I'm going to call this equation 2. Okay? And then we are going to look at conservation of energy for this problem. Okay? So we're going to call that E. Here, conservation of energy. And so then that means that the sum of all the energies in our system before the collision has to equal the sum of all the energies after the collision. We don't have any potential energies, just kinetic energies here, okay? So we've got 1/2 M1 V1 initial squared plus 1/2 M2 V2 initial squared equals 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. Okay? So again, all the masses are going to cancel each other because M1 is equal to M2, and each one of these terms has an M. Also, the 1/2s are going to go away as well. So we've got V1 initial squared plus V2 initial squared equals V1 final squared plus V2 final squared. Okay, and I am going to do a little trick. Okay, I'm going to move, again, all of our quantities to the left-hand side that deal with mass 1, all the quantities that deal with mass 2 to the right-hand side. So I'll have V1 initial squared minus V1 final squared equals V2 final squared minus V2 initial squared. Okay? And then, if you remember from your algebra class, which you all had to take as prereq, that if you see something that looks like this, a squared minus b squared, that's what we have right here, a squared minus b squared, you can factor this out to be a minus b times a plus b, okay? Because then if you go back and multiply those terms together, we'd have a squared. So if you go multiply the first terms together, that would be a times a squared. Multiply the outer two terms together, that would be plus ab. Multiply the inner two terms together, that's minus ab. And then multiply the last two terms together, that'd be minus b squared. Then we get back our a squared minus b squared. So this is how you can factor out, or factor, our a squared minus b squared. And we have that right here. We've got an a squared minus b squared on both sides. So we can factor this to look like v1 initial minus v1 final times v1 initial plus v1 final. And that equals, over here we'll do the same thing, v2 final minus v2 initial times v2 final plus v2 initial. Okay, and I'm going to call this equation 3. Okay, equation 3. So now what we can do is we can divide equation 3 and equation 2 in order to simplify things a little bit, okay? And so what I'm going to do is take equation 3 and we're going to divide it by what I have here as equation 2, okay? And maybe you've forgotten that you can play this little trick. So we've got this equation right here and we're going to divide it by this equation that we found right here from conservation of momentum. So on the right-hand side of this equation, the left-hand side of this equation, we've got v1 initial minus v1 final. That equals v2 final minus v2 initial. Okay? So if I look here, this term is the same as this term. This term is the same as this term. So then I'm left with v1 initial plus v1 final equals v2 final plus v2 initial, okay? And that's another equation that I'm going to call equation 4. Okay, so why did I do that? Well, we need to find v1 final and v2 final. Now, I have two simple equations where I have two knowns and two unknowns. If I have two equations and two unknowns, I can solve them in order to get me these two unknowns back here. So what we can do is we can come back over here. Equation 1 and equation 2 are the same equation. I just shuffle some of the terms around. So let's start with this one, first one up here. Okay, let's start plugging in some numbers. So v1 initial was 30 centimeters per second. v2 initial was minus 20 centimeters per second. That has to equal v1 final plus a v2 final. Okay, so then 30 plus minus 20, that's 10 centimeters per second has to equal v1 final plus a v2 final. Okay, and then over here, let's see, I can solve this for, I'm going to move my initial terms over to the same side. I've got v1 initial minus v2 initial equals v2 final minus v1 final. Okay, so what I can do is I can plug in 30 centimeters per second minus my negative 20 centimeters per second for v2 initial and v1 initial, and that has to equal a v2 final minus v1 final. Okay, and 30 minus negative 20 is 50 centimeters per second equals v2 final minus v1 final. Okay, so now I have these two more equations. I'm going to call these 4. Let's say I'll call this one 5 and this one 6. Okay, so now what we can do is we can solve these two simultaneously with each other in order to get V1 final and V2 final, okay? So I will do that in my remaining spot over here. I'm going to take equation 5, and equation 5 tells me that I have 10 centimeters per second has to equal a V1 final plus a V2 final, okay? And then with equation 6, I have 50 centimeters per second equals, I'm going to say, minus V1 final plus a V2 final. I can add these equations together, okay? 10 plus 50, that's 60 centimeters per second equals, we've got V1 final minus V1 final, so that's 0, plus V2 final plus V2 final plus 2, a V2 final. So if I divide both sides by 2, I get that V2 final equals 30 centimeters per second. Okay, finally I found, after all of that work, in our elastic collision, conservation of energy, conservation of momentum, that perfect conservation of energy, perfect conservation of momentum, that V2 final is 30 centimeters per second. So if I take that and I plug it into any one of these equations, equation 5 or equation 6, then I'll get what V1 final is. So let's do that right here. If we've got 10 centimeters per second equals a V1 final plus 30 centimeters per second. So we subtract 30 on both sides. So then we'll have minus 20 centimeters per second equals V1 final. Okay, so what happened here in our perfectly elastic collision? Energy is perfectly conserved. Momentum is always conserved in a collision. Our first mass with 30 centimeters moving this way, our second mass with 20 centimeters moving that way. They collide. They conserve energy. They conserve momentum. After the collision, they both end up, they collide, and then they both go back the opposite direction from which they came. But they collide. They have to conserve energy, okay? So when they pop off, the one over here, M1, actually has a velocity of minus 20 centimeters per second in this way. And our mass 2 now has a velocity of 30 centimeters in this direction, okay? So you can think about them kind of as this one's coming in with 30, this one's coming in with 20. They collide and they exchange their speed, okay? And so when we pop off in the other direction, M2 is going to go off with 30 centimeters, and M1 is going to go off in this direction with 20 centimeters. Okay, so that's how perfectly elastic collision will work between two objects. If you had a bunch of marbles lined up in a row, like what we have in part of your at-home lab for these next few weeks, if you have, let's say, 3 marbles on one side of a little channel and 2 marbles on the other side, if you flick those 2 marbles in to smash into your 3 marbles that are stationary, what will happen is that they'll exchange energy, they'll exchange momentum. You've got 2 marbles coming in, hitting the 3 marbles here, and then what's going to happen is that you're going to end up with 3 marbles left over stationary, and 2 marbles are going to pop off in the other direction. Okay, that's again a conservation of energy, conservation of momentum, and something that's almost like an elastic collision.